So, in the last video, we learned about the different energy levels of the hydrogen atom. Now, in this video, we'll be learning about the spectrum, that is the hydrogen spectrum. So, what is that? Whenever the electron belonging in any higher state, higher or excited state, jumps to any lower energy level state, it loses some sort of energy in the form of light. Say it jumps from number 2 to number 1. So the energy gap is the energy lost by the electron, and which is equal to the energy of the light, that is the photon, which is given by h nu or hc by lambda. Now we need to find a ready-made formula from which we can find the wavelength for the electron jumping from any orbit to any other orbit. So to do that, we need Rydberg's equation. So let's arrive to that. So the idea is, say the electron initially belongs to orbit number ni. So initially it is in orbit ni and it jumps to an orbit nf. Okay, so we need to find the energy gap of these two orbits. So we'll be using here this formula, En equals to E1 by n square. We saw it in the last video. So the initial energy level, that would be EI equals to E1 by ni square, and the final would be EF equals to E1 by nf square. Okay, so now the basic idea is the energy gap is equals to hc by lambda. So let's do it. Del E or hc by lambda equals to del E. Now let's put the values here. It will be EI minus EF. Remember this carefully, that the electron always jumps from higher state to lower state. So EI will always be greater than EF, and in the same way Ni will always be greater than NF, higher state to lower state. So if we put the values here, these two values in this one, we'll have E1 as common, Ni square minus NF square. Yeah. Now there is a little bit of a problem, which is if Ni is greater than Nf, then this whole thing will be negative, and we know that wavelength cannot be negative, though it will not be of such a problem because Ei itself has a value negative 13.6, so ultimately it will be positive. But we want a formula where we can put the values of Ni and Nf and we will get the result. So to do that, what we'll do, we'll take a negative in common. So it will simply be Nf square minus Ni square. Now, so let's get these two down to that side. We'll have 1 by lambda equals to negative E1 by hc 1 by nf square minus 1 by ni square. Now look at this very carefully. This E1, H and C, all of them are constant. So by combining them, we'll get another constant which is written as R. Okay, now this is the famous equation, Rydberg's equation, which you need to memorize very well, and this constant R is the Rydberg's constant. Okay, and you also need to memorize the value of R, 1.297 into 10 to the power 7 meter inverse. Yeah, now look at this equation very carefully. You need to memorize this equation very well to get the values of wavelengths of different series or something. You don't need to memorize the values of different series, just this one, and you will be doing everything well. Okay, so let's move on and see for formulas for different series. Okay, so now we need to learn about the different spectral lines and the names of the series. So what are those? Depending on the final state to which the electron jumps, there are different series named, such as Lyman, Balmer, Paschen, etc. So at first, when the electron jumps to the first energy level, that is the ground level, from any of the higher levels, say from 2 or 3 or 4, then the series is called Lyman. And similarly, if the electron jumps to the second level, second state, from any of the higher, it will be called Balmer. Similarly, the next one would be called Paschen, and it goes on and on. Now you need to find the different wavelengths for different member of each series. So you'll have to make different formulas for each of the series using the main formula. Now remember it that you don't need to memorize the formulas for different series. Simply memorize this one and we'll be getting to the formula for any series using this one. So to do that, what you need to actually memorize is the sequence of the series, nothing else. Let's write down the sequence of the series. So at first it comes Lyman, then Balmer, then Paschen, then Brackett, then Fund, and then Humphrey. That's all. So it's like this. When the electron jumps to the first orbit, that is Lyman. So you need to remember, for Lyman, final energy level is 1. For Balmer it's 2, 3, 4, 5, 6. So that's all you need to memorize. Now say we have to find the wavelength for Lyman series, and the formula for Lyman series would be, idea is it jumps to the first orbit, that is for Lyman final is 1 and initial would be anything greater than 1, that is 2, 3, etc. Okay, now simply put these values in the main equation, that is the Rydberg's equation. You will get formula for Lyman, 1 minus 1 by n square. Yeah, say let's take any series arbitrarily, say we take Brackett series. So similarly for Brackett, as we can see, Brackett is number 4, so the final orbit is number 4, that is NF is 4, and Ni would be anything greater than 4. It can be 5, 6, 7, etc. Okay, so the formula becomes 1 by r 1 by 4 square, that is 16, minus, yeah, so it was simple. Okay, so now we'll do a basic numerical problem. Say we are told to find any spectral line, the wavelength of any spectral line of any given series. Say I'll take a second spectral line of Balmer. We have to find the wavelength of this one. So as we know, Balmer comes second after Lyman. So for Balmer, the electron jumps to the second energy state, and for the first spectral line it should come from third orbit, and for the second it will be from fourth. So we have n final is 2 and n initial is 4. Now we'll put these values in the main Rydberg's equation. Let's see what happens. So we have 1 by lambda equals to yeah. So now if you put the value of R in a calculator, you can easily calculate the result. Okay, so let us check another way, a little bit faster way. In this way, we'll be using this formula. The energy gap is related to wavelength by the equation del E equals to AC by lambda. And the shortcut you know that you have learned in the chapter photoelectric effect, that energy can be found by using this relation 12400 by lambda, when lambda is taken in angstrom and the energy is in electron volt. So we'll be using this relation to find the wavelength. Okay, now as we know it, the electron jumps from the fourth orbit to the second orbit. The fourth orbit has energy negative 0.85 and second orbit energy is 0.34, and these are in electron volts. So we need to find the energy gap, which is 2.55 electron volt. Now simply put it in this equation, you will have your answer. So it will be 12400 by 2.55. okay, so it will be, do it this way. If you have 3 here, it will be 12,000 by 3, 4,000 something. If it was 2, it will be 6,000 something. So since it is 2.5, it will be anything in between 4,000 and 6,000. So let's take it rounded off result as 5,000 angstrom. Now note carefully that this result isn't an accurate result. Don't do it when you are told to find the wavelength in your boards exam. Say you are solving MCQ and you have been given 4 options and you have to just tick the right one. In that case you can do it this way. Just get an estimated value and just check which one is the closest to it, then simply tick it. And in the boards exam, what you need to do is this one. Okay, put the value of R, then calculate and find the exact value of lambda. Okay, so practice this process, the second process that we saw, to get the work done faster, and you'll acquire it easily. So let's move on. Now let's see a very standard question. Say you are told to find the longest and the shortest wavelength of any given series. So the basic idea is, we know that energy gap del E is hc by lambda, and so that energy gap is inversely proportional to lambda, or lambda is inversely proportional to del E. So in order to have the longest wavelength, we need to have the shortest energy gap, and for the shortest wavelength we need to have the longest energy gap. And now if we draw the energy levels roughly, we'll see that this is 1 2 3 4. Now see that for any given level, the shortest energy gap is from exactly the next one. Say for 2, the shortest gap is the next one, that is 3. For 1, the shortest energy gap is from 2. So the idea is to have the longest wavelength, you need to have the electron coming from exactly the next orbit. So in this case, Ni would be the next one. that is it falls from the next orbit. And for shortest lambda we need to have the maximum energy gap. Now as you can see, the maximum energy gap for any given state is from exactly up here, that is n equals to infinity. Okay, so in this case the electron needs to jump from ni equals to infinity. So this is the thing you need to remember. Now say you are told to calculate longest and shortest of Balmer. Okay, let us calculate longest first. So for Balmer we know that it is at second, so n final would be 2, and as we saw for longest, n initial is next one, that is 3. Now simply put these values in the main equation and we'll have 1 by lambda equals to r 1 by 4 minus 1 by 9. It will be, yeah. So now you can simply put the values in the calculator and get the exact value of lambda. And for shortest, NF is 2, and as we see here Ni would be infinity. Okay, so put the values in the equation. Okay, so again you can get the value from the by putting it in the calculator. So let me do this thing in a different way, in a shortcut that we learned earlier as well. Let's see. Now in this shortcut process we see, say at first we calculate the longest wavelength. The electron falls from jumps from the third orbit to the second orbit. The third orbit having energy negative 1.51 and second orbit having energy negative 3.4. So exactly like we did in the previous problem, we need to find the energy gap, that is .8 electron volt, 89 electron volt. Hence lambda would be 12400 by 1.89, and we will get the value in angstrom. So it should be, say if it was 2, it will be 6200. It is less than 2, so it will be a little greater than that. Let's take it 6500. This is estimated result. And for shortest, the electron jumps from infinity, which has energy 0, to second orbit having energy 3.4 electron volt. Also obviously the energy gap is 3.4 electron volt, hence lambda would be 3.4. So now calculate it this way. If it was 3, it would be 4000 something. If it was 4, it would be 3000 something. So it should be in between 3000 and 4000. So let's take it as 3500, this much angstrom, and practice this one for increasing your speed for the competitive exams. Okay, so let's move on.